Check what's next on the list. Oh, I think that's it. Okay. I'm gonna come back to meso compounds here for a little bit. So, how would I define a meso compound? Well, the meso compound has multiple, most of the examples you will meet with two stereocentres. Tetrahedral, 4 different groups around it. But the stereocentres must bear a certain relationship to each other. If I asked you what's the configuration of the carbon on the left, first priority, second priority, third priority, H behind the board, that's good. First, second, third, I do this is the R stereocenter. What's the configuration there? Well, if I look, these are mirror images. So if this is the R, this must be the S. I can work it out. I shouldn't have to, but I'm going to work it out. First, priority. Second, third. The H behind. 1, 2, 3. That is anti-clockwise, or S. So to be meso, I need to have 3 things. I need to have typically 2 stereocentres, which are symmetrically substituted, same groups, that have opposite configurations, R and S. Right? They must be R and S. And you know, the way some people look at it, which, you know, is that if I look at these 2 groups, this is the meso compound, have opposite configurations, and of course they do. And so really, one of these sites cancels the activity of the other site. Okay? And that reminds me, there's a point I'm about to mention. So, 2 things left. If I take this compound and I see it has 2 stereocentres, so I'm expecting a maximum of 2 to the 2, 4 stereoisomers. Let's draw them out. And I tell you what, before I do that, let me do a different case that's similar but slightly different. So let's say I had this compound, so OH and methoxy. Alright, 2 stereocentres. I expect a maximum of 2 to the 2 or 4 stereoisomers. What do they look like? So I'm just going to go ahead and draw them like this. And I'm just going to plot the groups on. So I'm going to go ahead and draw pairs of them. And I'm going to draw 4 because I'm expecting 4. Okay. So let's say I start off by putting the methyls here. So methyl, methyl. I'm going to put the H's behind for ease. I'll put the OH here and the OME here. Okay? Great. This represents a mirror. It's a different color. That represents a mirror. This represents a mirror between the different species, which means the mirror image of this will have the methyl here, the H down and behind, the OME out and in, down and in front. Far from the mirror is the OH, down and out, the H down and behind, and the methyl here. Okay? What's the configuration here? First priority, second priority, third priority. H behind. So I'm going to go this way, right, which is anti-clockwise. This is S. First, second, third, the H behind. I'm going this way, this is R. In the mirror, if this is R, this must be S. It's the mirror image. And if this is S, the one with OH, this must be R. Now it has to be that way, but I'm just going to work it out for you anyway. 1, 2, 3, H behind, anti-clockwise, S. Right? 1, 2, 3, clockwise, R. Okay. What I'm going to do now is keep the methyls up top again, but I'm going to swap the OH and the H. I'm going to put the OH behind the board, keep the H in front. I'm going to leave this where it is. And so what is this one? Well, if this one was S, and I've swapped the OH and the H, then one interchange, it's now R. I didn't touch this one at all, so this is still R. When I draw the mirror image, methyl, H, methoxy, close to the board, and then methyl, OH, H. If this was R, this is S. If this is R, this is S. So in other words, if there are only two stereocenters, and the possibilities are R and S, you're going to have, okay, if you have a, let's back up. So you only have options of R and S. If you only have one stereocenter, you're going to have R and S, two enantiomers, two stereocenters. If you have two stereocenters, your possibilities are RR, RS, SR, SS. That's it. If you have three, it could be RRR, RRS, RSS, SSS, SSR, and so on and so on and so on. You'll end up with 8, 2 to the 3. So these are my 4. SR. Now, if I start from the hydroxy, it's SR and RS, RR and SS. Those are my 4. What's the relationship between them? If I call this species A and B and C and D, what is their relationship? Well, the relationship between, so let's say A, B, C, and D, and then A, B, C, and D, and then B, B, C, C, D. What is the relationship between A and B? And I'm going to choose from the terms same, enantiomer, diastereomer, or other. The X means the same. So A is A, B is B, C is C, and so on. How are A and B related? Well, they're not the same. Because in one, the group with the hydroxy is S, here it's R. So they're not the same. They are mirror images of each other. So A and B are enantiomers. What about A and C? Well, they're not the same, because here the OH group was in a carbon that's S, here it's R. Are they enantiomers? Well, no. The enantiomer of the SR compound, the enantiomer of the SR compound is the RS compound. So these are not mirror images, right? If I take this molecule and I pull it out of the board and I lift it, this side with the methyl H and the OH reflects into that one perfectly. This one doesn't. The methyl reflects into the methyl, but the back OH reflects into the front methoxy. That's not valid. So they're stereoisomers, but they're not mirror images of each other. These are diastereomers. So A and C are diastereomers. What about A and D? Well, again, they're not enantiomers, because the enantiomer of the SR should be the RS. So quite frankly, these two, quite simply, these are diastereomers as well. Because again, they will be stereoisomers, which are not mirror images. So A and B are enantiomers. What about B and C? Well, the enantiomer of the SR compound is the RS compound. RR must be the diastereomer. So B and C are diastereomers. B and D are diastereomers. C and A, we already said, are diastereomers. C and B, we already said, are diastereomers. C and D are enantiomers. They're mirror images of each other. So these are enantiomers. A and D, diastereomers. D and B, diastereomers. D and C are enantiomers. So this is where when we talked about if you have n stereocenters, you can have a maximum of 2 to the n stereoisomers. And what that ends up being is you end up getting sets of enantiomers. Right? So for every stereocenter, you would generate a set of enantiomers. So technically, if I have 3 stereocenters, I'll get 3 sets of well, that's, yeah, it's not quite right. Okay, okay, let's now go to this compound. I'm going to convert this species into the diol, so that I end up with a situation where there's a potential for symmetrical substitution of the stereocenters. So I'm going to go ahead and change all the methoxys into OHs, all the methoxys into OHs. And let's see what happens instead. The configurations will remain the same. SR, RS, RR, SS. But here's the thing. If I take that molecule and I slide it through the mirror, it superimposes on that one. Right? That methyl comes here, this methyl comes here, this OH comes here in front of the board, H behind, OH in front and to my left and bottom, H down and to my left and bottom. And behind the board. In other words, these are the same. And I would not call it the SR or the RS, that's meaningless now. It depends on who you call first. I'll just call it, it's one species, which is meso. Now, these are different. Because if I slide this through the board, if I slide that to the board, the methods will superimpose, but the H and the OH here, they don't. Even if I turn it, let's see for a second. So I'm going to take this molecule with the OH in front here, and I'm going to turn it this way. So now this front OH goes onto the back H. They don't superpose. So these are two unique compounds. So although I have two stereocenters, in this case I don't get 2 to the 2 stereoisomers. I only get 3. I don't get 4, I get 3. And that's because I make a meso compound. Okay? And what should have been 2 enantiomers doesn't end up that way. They end up being the same species because of that planar symmetry. The last point I'll make is that a meso compound is a meso compound. And it doesn't matter in what conformation the meso compound is. I mean, this compound has certain properties, right? And so, even though I can see the mirror plane in this conformation, and I don't see it in the other, these still have the same configuration. And as long as the configurations are opposite to each other, and there's symmetrical substitution, I am meso. It doesn't matter what my conformation is. So sometimes you will get a meso compound in which the groups are not aligned along the mirror plane. And that's okay, right? For example, if I rotate, so the OH replaces the H, the OH comes here, and then the H replaces the methyl, and the methyl swings out to make the H. So it was OH, H, methyl. Right. So it was OH, H, methyl. So I'm going to move the OH here, the H gets pushed out here, and the methyl gets pushed up here. Okay. So now that has rotated. And if I look at it, there's no longer a mirror plane. But let's find the configuration of this carbon. First priority, second priority, third priority. With the H in front, so I'm going to invert it. So first, the second, the third looks R, but it really is S because the H is in front of the board. Well, that's still meso. Even though I'm not seeing the mirror plane, that is still meso. Okay? Alright. Last one. Chiral compounds have a particular property, which is that they rotate the plane of plane polarized light. And we'll pick up some more of this in the next lecture. But when a molecule is devoid of sigma, that means it is chiral. Which means that molecule is going to be what we say optically active. An optically active molecule is one that rotates the plane of plane polarized light. It rotates, that means it rotates plane polarized light. So plane polarized light. Plane polarized light, and I'm going to do a very simple description here, because you can make it more complicated. Imagine a pencil of light traveling away from you, or coming towards you, doesn't matter. So here's the beam of light. Light is a transverse waveform, so the oscillations occur in every possible plane perpendicular to the direction of propagation, right? So if the beam is going this way, I have an infinite number of planes of oscillation perpendicular to the direction of light is traveling. It is possible to pass such light, normal light if you will, unpolarized light. It is possible to pass such light through a filter that filters out all the planes of oscillation except for one. So if I pass this through a polarizer, and polarizers could be as simple as a Polaroid lens, so that the glasses that were are still used today. And what you get is oscillation in only one plane. What that does, by the way, is it decreases glare and increases sharpness. So these are common uses. People wear them with sunglasses, and when you fish, you can see the fish in the ocean, or whatever. If you pass plain polarized light, if it impinges upon any compound, the plane of light is rotated. Clockwise, anti-clockwise, it's rotated. But if you pass that light through an achiral molecule, so here's let's say it's a sample containing tetrachloromethane. So these are this tetrachloromethane. Tetrachloromethane is a CX4. It does not have a stereocenter. It does not, more to the point, it does have mirror planes, and therefore it's achiral. It does not cause net rotational plane polarized light. Why is that? So let's say light enters my sample of CCl4, plane polarized, but ends up coming into the molecule and hits the molecule and gets rotated 10 degrees clockwise. Well, in the sample of an achiral compound, you are bound to find the mirror image. It's a statistical certainty. So you can imagine the light comes in, gets a 10-degree rotation in one direction. Before it leaves the sample, it is going to meet the mirror image, not the enantiomer, because it's not chiral. It's going to meet the mirror image that's going to rotate it 10 degrees in the other direction. So 10 degrees clockwise plus 10 degrees anti-clockwise equals 0. So really, when light impinges on a sample of an achiral compound, the light undergoes rotation, rotation, correction, correction, rotation, correction, rotation, correction. It is a statistical certainty it will meet the mirror image of everything it meets before it leaves the sample, causing no net rotation. Rotation, correction equals no net rotation. But if that light enters a sample of a chiral compound, right? So I have a sample of a pure chiral compound, S2-butanol, or R2-butanol, not both. When the light hits this molecule and undergoes a 5-degree rotation anti-clockwise, in the pure sample of this compound, it will never find the enantiomer, because it's not there. So the light beam undergoes rotation, maybe some more rotations, never a correction. So when the light passes through that sample, there is net rotation. So chiral compounds are said to be optically active because they cause net rotation of plane polarized light. Okay? And if it rotates light clockwise, we say the sample is plus rotatory, or sometimes dextro-rotatory. Or D, lowercase d. There's a big D used in stereochemistry. It means something entirely different. You see it in biochemistry. If it rotates like counterclockwise, we say it is minus rotatory, or it's levo-rotatory, or it's L for levo. D for dextro, L for levo. Dextro means right, levo means left. It's a Latin root. So it turns out, for example, that R2-butanol is either plus, or D, or it's minus. And here's the point. We don't know which it is unless we do the experiment. There is no connection a priori to configuration and direction of rotation of plane polarized light. Some R compounds are plus. Just as many are minus. Some S compounds are plus. Just as many are minus. But what I do know is if you're R and minus, then the S enantiomer is plus. Right? So if the R is plus of a given compound, the S is minus of a given compound. Okay, we'll stop there and pick up from here next day.